we left off after an example. We went through and we said, we have this charge density and we have a way now to calculate total charge in things. The thing could be a volume, the thing could be a surface, the thing could be a line. Then correspondingly, we went through a line charge example, a surface charge example, and a volume charge example, and that's where we left off last time, okay? Now, we want to build up to something. This is a little abstract here, but I want to give you the big picture where we're heading first. We want to be able to figure current out. We just want to be able to figure out current. Current through a surface, though. We want to be able to say for any surface, it could be like a three-dimensional thing. Imagine some kind of like a blob, or it could be like a wire like this. And basically, if we defined a surface, we want to be able to say how much current is passing through that surface. So we got to build up to that first. So this is how we're going to do it. We're thinking about a tube. These little green dots, you can think about those as the charge carriers, right? Think of them as electrons or positive charges, whatever you want to think about them as. And this volume charge density is rho v. Remember rho v, what are the units of rho v? Yes, because of the v. So you got it for rho, you just got to remember the coulombs part, it's coulombs per something. And then you just have to look, is it subscript v? If so, it's coulombs per meter cubed. Is it s? Then coulombs per meter squared. Is it l? Then it'd be just coulombs per meter, okay? So what does that really mean? Just think about it as like the concentration of charges in the thing, okay? Because coulombs is charge, right? So coulombs per every cubic meter, right? We're talking about current. So what is current? Current is charges moving, okay? So these little green dots, think of them as the charges. They are moving to the right. They are moving at a velocity u, okay? Now u is a vector here, but for temporarily, we're gonna not worry about it being a vector. And the reason for that is because everything's gonna be lined up and then we're gonna make it into a vector, but we'll get there. So if we think of a period delta t, and we want to think about how far the charges move, well, if you know the velocity, then this is really just like saying, you know, you're driving at 65 miles per hour on the 405, and you drive for a half an hour. How far did you go? That's really all we're saying here, okay? So that gives us our delta L. And then we can say, well, all right, let's throw a bunch of other stuff here and let me explain it. So if you consider just some cross-sectional surface like this one shown here in the middle, and you ask yourself the question, how much charge passes through that imaginary cross-sectional surface, okay? Another way you can think about that in a certain amount of time, delta t, okay? Ultimately, just another like spoiler alert here, where we're going is we want to figure out current, right? Anyone remember what the units of current are? Not amps, but what an amp is? Per second? Yeah, it's a coulomb per second, okay? So what do we really want out of this? We're really looking to get like a Q divided by a T, so then we get a current, all right? So we already got our Q, and what is that really saying? Well, that's the amount of charge that crosses the tube's cross-sectional surface, okay? So it's really how much crosses this. And another way you can think about that is kind of think about this as a volume, like how much of the charges flow through this surface. We can think about that as whatever the volume charge density is times the volume of this. So kind of imagine that cross-sectional surface kind of extended down over the time period delta t. Bit of an abstract thing to think about. But that's how much charge passes through this surface over a time delta t, okay? So how much charge is that? Well, it's rho v times whatever this volume is. And you'd say, well, what is this volume? Well, it's delta L long. So that gives you this dimension. And this face, which is the same as that face, it's like a little cylinder there. The volume of that cylinder is delta V, which is really delta L times delta S, okay? All right, and then we just have to, at that point, go, All right, well, if we have a delta L, we just said what delta L equals. It equals U times delta T, and this is good because now we got a delta T. We kind of started with the Q. Now we're going to have a time, so now we could potentially rearrange it, get a charge divided by time, and get it in terms of an amp, which is a current. Okay, so then if we plug that into there, the U delta T, U delta T, we still have our rho V, and we have our delta S, then we have this thing. Let's just check the units just to see what we're doing here. Okay, you already said that the units of rho V are coulombs per meter cubed. What would the units of U be? Yep, it's a velocity, it's a speed. What would the units of delta S be? First of all, think about what delta S is. What do we think it would be? What is it? What does delta S represent? Yeah. So if it's a cross-section area, what would the units be? Yep, it's an area, so it's meters squared. And delta T would just be seconds. All right, well, let's cross out some stuff here. So you can see here we've got an M times an M squared. That's going to be an M cubed. It's going to cancel out with that. Seconds going to cancel out with seconds. We're left with coulombs, which is good because here we are a charge. So that's good. Okay, now we didn't talk about it, but this delta S, what would the surface normal to delta S be? What would the direction be relative to, let's say, the U? What do we always say the directions for surfaces are? Normal. It's a normal. So the normal to that delta S surface, which is like the cross-sectional area, right? Like the end of the pipe, it's in exactly the same direction as U. So that's why we've dropped out the vectors here. Okay, why everything in this equation is written in non-bolded and italicized letters. That's because everything's perfectly aligned, but we want to make this generic for any situation. So we could have the U, we could have some, some blob material, right? It doesn't have to be a nice pipe. U could be going in this direction, and you could define some other surface in some other direction. And so the U would be in one angle, and the normal to the surface, which is the direction of delta S, could be in a totally different angle. And we want to figure out how much current is going through that ultimately. And if you remember when we introduced the dot product, I always said think of the dot product as how well aligned two things are, like how much, when we talked about it in another context, kind of how much is going to flow through the one thing. If you remember, we talked about that. So basically, to make this generic, we just have to switch the U into being a vector, because it's got that red arrow, right? And the delta S into a vector, where the delta S vector is the normal to whatever you define the surface to be. Boom. It's exactly the same as before, but with a bolded U and a bolded delta S, representing vectors, meaning they have a direction, not just it's not just a number. And in terms of a magnitude, it also has a direction. This is what we said. We said the direction of the surface is normal to that surface. That's what the n hat is. And then the non-bolded delta S just means that's just the actual area of the cross-sectional piece, okay? Okay, so let's rearrange this then. So let's say we just bring the delta T over there, right? I said we want a Q over T, coulombs per second, to get us in terms of amps. So if we do that, then we'll get this delta Q over delta T, and we're just left with the rho V times U dot delta S. So if U, the velocity of the charges, is perpendicular to delta S, then none of the charges flow through delta S, okay? It's like you're wading in a river, the water is flowing down the river, the water molecules represent the U, so they're flowing down the river, and you have like a fishing net, and you want to know how much water is flowing through your fishing net, okay? If you put that fishing net in, so it's kind of like perpendicular, right? The normal to that surface bounded by the edges of the fishing net is going to be directly aligned with the flow of the water. You get a maximal amount going through the kind of hoop of the fishing net, right? As you turn the fishing net and you kind of angle it more and more like this, well, now there's kind of less area for the water to flow through kind of the hoop of the fishing net, right? And if you made it perfectly parallel, now the normal straight up, now none of the water can flow through. It's going to hit like the edges of the fishing net or something like that, right? And what would that represent in terms of this dot product? Well, U is straight the direction of the water down the river. But in this case, now the normal to the surface is straight up. So we have a 90-degree difference between the U and the delta S. Remember, dot product has the cos of the angle between the two vectors in it, cos of 90 is 0. So that would really represent no water flowing through the net. Or in this case, you know, if we extended this all the way like this, because you can see it's angled here, if you went so it's totally flat, no charges would be flowing through the surface. That's all that it means. So this is what we're left with. And then you can say, well, how did we get over here? We just said J equals rho V times U, just a definition. That's the J in Maxwell's equations. Anyone remember the last of Maxwell's equations, the one at the bottom? It's called Ampere's law. It's the curl of H equals J, that J, plus the partial derivative of D with respect to T, but we're not worrying about that last partial derivative of D with respect to T. We are worried about that J though, and this is that J. So what are the units of J? Anyone remember units of J? Units are very useful to help you know if you're kind of on the right track of things. Yeah, amps per meter squared. So it's called a current density. Its units are amps per meter squared. So I guess we should check that. So we have coulombs per meter cubed. That's the rho V. U is meters per second. So the 1m here is going to cross out with that 3. It's going to be 2. And if I just rearrange it, I could write it in coulombs per second per meter squared. A coulomb per second is an amp, amps per meter squared. Amps current, meter squared is an area. So it's like how much current over the area is there? Think about this. Does this make sense? Rho V, that's your charge density, your volume charge density. Coulombs per meter cubed. It's like, think of a 1 meter cube box. How many charges are in that? What's your total charge in there, right? Times U, the velocity of the charges. So if you wanted a current, you could have a few charges flowing with more velocity or more charges flowing slowly, okay? Okay, so that's J. This allows us to calculate I, the current, but we want to make this generic. So rather than looking at this specific thing, we can say, well, if it was any old surface, right? That one was kind of limited to this cylindrical pipe kind of thing, but we want to make it very generic. It's kind of going to be a theme that we're going for here, where it's like you might have learned like Ohm's law for circuits, and that perfectly applies to circuits, but we're shortly going to have a more generalized form of Ohm's law. And here's our generalized form to calculate the current through any surface. How do we do it? Well, if we're really doing it for any surface, we need to break that surface up into little pieces, ds. And for each one of those pieces, we do what we did for the last one. We do j dot ds, right? J dot delta s in this case, but if in that case, we need to break it up because we want to make it for any generic surface. Break it up into little chunks. Each chunk do j dot ds. J dot ds tells you how much current is flowing through that ds. Then we integrate it over the entire surface. Okay. Okay, now, there's two types of currents. When you think of current, I'm not sure what you think about, but if you think about it in terms of circuits, like your circuits class, like 240, right? Well, essentially what you're doing there is it's normally like a wire, maybe made out of copper or aluminum or something like that. It's a metal, it's a conductor, has high conductivity, which means its electrons in its outer shell are loosely bound to the atom. And under the influence of an electric field from a voltage, you're able to push those electrons around, okay? So if you set up an electric field due to a voltage, you can make the electrons move from atom to atom to atom, okay? That's one type of current, okay? That one is called conduction current, okay? The electrons that emerge from the wire are not necessarily the ones that entered the wire on the other end, okay? So it's like you have movement of them, but it's not like one that's moving all the way through. The other type is called convection current, and that's when you actually have all the charges kind of moving together. So an example of that is if you had a cloud in the sky, okay, and it had a bunch of negative charges in it, say, or positive charges, and the wind blew that cloud, okay? Or old style CRTs, like cathode ray tubes, I believe the way they worked was it was kind of like firing electrons at a screen. And so those electrons are really moving from one point to another point. That's a current in itself too. So subtle difference that for us isn't really gonna matter too much. It's more just like file it away, that it could come in these two different forms where it's like all the charges are moving together, or it's this kind of like domino effect, let's say. Okay, that's that. What did we just do? We introduced Maxwell's equations. Then we saw, well, Maxwell's equations have, all right, Maxwell's equations. We had the first equation. It's called Gauss's law. And it was the one that's the divergence of D, which is the electric field thing, equals rho V, okay? So we just dove into more about what rho V is. And we saw that we can have a rho V, we can have a rho S, we can have a rho L. And we saw that from that, we're able to figure out how much charge is in something, the something being a line, a surface, or a volume, okay? If we carried on, the next equation, Maxwell's equations, are the curl of E equals negative time derivative of B with respect to T. We haven't really done anything with that one yet. The next one is the divergence of B equals 0. This is sometimes called Gauss's law for magnetism. And that's the one that means there's no such thing as like a point, the equivalent of a point charge for magnetic stuff. All magnetic fields are in loops. There's no like point where they generate from or end at. Unlike a point charge, like a positive point charge, the fields all emanate away from that positive point charge, all right? We haven't really done anything with that one yet either. The last one is the Ampere's law that I said before. The curl of H, the curl of the magnetic field, equals J plus that little piece of magic that Maxwell added, the displacement current term it's called, but we're not dealing with that. The reason why we're not is because it's a time derivative and we're not letting anything change with time. So it equals 0. So we really, for our purposes, for electrostatics and magnetostatics, we just have that the curl of H equals J. So we want to talk about J for a little bit. That's what we just did. We just defined what J was. And now we know how to use J to calculate the current through any surface. Okay. So we really talked more about two of the pieces of Maxwell's equations and how to do something with them. Calculate the total charge, calculate the total current. Now we want to move on and talk about the electric field. Okay. By the end of it, we're going to kind of hit all of them, all of those things in Maxwell's equations. The E, the D, the rho V, the H, the B, the J. Okay. We're kind of starting with the E now. This should look familiar. You probably heard about Coulomb's law maybe since high school. Okay. Maybe you've seen all of the stuff that we're going to talk about. And if this is kind of a review, some of this may be a review from Physics 220B or equivalent that you took, that's great. But it won't be for everyone. So we're going to cover it to make sure, well, especially if you want to carry on and do more advanced electromagnetic stuff, that you've got a good solid foundation to go on and take the next course in electromagnetics, which would be 571. Okay. The only requirement for 571 is 370. Even though it's a 500 level course, don't let that scare you. As long as you have the prereqs, it's fine. You Half the class is normally master students and half the class is undergrads, but don't let that scare you either. You'll be fine if you work hard and you did well in 370. You'll be okay. Depending on who teaches it, normally either I teach it or Professor Rangarajan teaches it. We both, I believe, now use, well, I know I do, and I believe he now also uses the same textbook. Basically picks up where we stop off here, like in chapter 6 or so, okay? That course is only offered, this is just a word to the wise, just as you're going forward. When you get into the 400 and definitely the 500 level courses, they're not offered every semester. So you need to plan things a little more. For instance, 571 is only offered in the spring semesters. So if you want to take it in the fall, if you plan to take it in the fall, you can't. It's only in the spring, okay? Other classes like 572, which is a bit more along the lines of the first half of this class, that's only offered in the fall, okay? So just take that, into account, and at some point you'll have to do your senior electives form, and you'll have to think about it then to get that approved, okay? Okay, now we're talking about electric fields. This is the simplest version of Coulomb's law. Electric field intensity, that is the E that's in Maxwell's equations, and equals R hat Q divided by 4 pi epsilon R squared. It's in volts per meter. Careful with your units here. The E is easy for units, volts per meter, and the H is pretty easy for units too. It's amps per meter, but some of the other things could catch you. So, don't take any chances if you're not 100% sure you've got them memorized for midterm 2 and final exam. Just write the units down on your formula sheet and somewhere highlight or asterisk and just say, go through units before submitting exam. And just in the last couple minutes, just go through all the questions, make sure the final answers have units and put what the units are, okay? All right, E is it's bolded. That means it's a vector. R hat. R hat, that implies a spherical coordinate system. Think about this charge being at the origin. R hat, capital R hat in the spherical coordinate system points away from the origin in all directions. So the electric field points away from this charge in all directions equally, okay? Think of like the sun radiating light equally in kind of all directions or something like that, except for something extremely tiny, like a point charge. Q is the charge. Q has units of coulombs. It's just the charge. If Q can be positive, Q can be negative. If Q is negative, what would the field lines look like here? How would you redraw this? Yeah, it would be a sink. And how would the blue lines look? They'd all be pointed in. They would all be reversed around, so the arrows are pointing in. If you calculated the divergence of that, you should get a negative number because it's acting like a sink, okay? So that's R hat, that's Q. 4 pi epsilon, that's our same epsilon. That is the permittivity. Epsilon is epsilon naught, epsilon R, where in this context, it means the region where the electric fields exist, whatever material that is. It doesn't have to be air or free space. It could be water, it could be whatever, right? So that is, what is the epsilon R for the material in which these electric fields are living, where they are. R squared is the distance, the physical distance from the charge to wherever you're trying to figure out what the field is, okay? The R hat is the direction from the charge to wherever you are considering it being. And as I said, that can kind of be in any direction, right? Because it radiates equally in all directions. So that's that. That is Coulomb's law. We got volts per meter. R is the distance. R hat radially away. This is important. Very often in the quizzes on midterm 2, final exam part 2, you could easily be asked a question of, there's some point charges or something. Find the force on a test charge located at this point. Really what you have to calculate is the electric field, and that should be bolded. That's my mistake. So I'll just draw an arrow over top because that is the same E as that. So it's a vector. If you're ever asked to calculate the force, it's just the electric field times the charge. Okay. So in other words, if you had some electric field due to some other charges or something like that, the type of the question you'd get asked would be, find the force on this other charge located here. And so what you would do is you'd figure out what is the electric field there at that test charge, that would be E. And then Q is what is the actual charge on that test charge. It's in coulombs, okay? That's how you figure out force. So really, to figure out force, it's really a simple, calculating the electric field is kind of everything. After you calculate the electric field, you're just multiplying it by a number, okay? Well, let's make it a little more complicated. That was with a 1 point charge. 1 point charge, you can consider that point charge as if it's at the origin, okay? Because you can define the origin kind of however you want. The important thing is how far away you are from that point charge. So here, although it's not written, it's kind of implied that this point charge is at the origin. But if we have multiple point charges at different locations, well, now we can't really make like that the origin or that the origin or something like that. So normally we have a more, we have a coordinate system where all of these, the positions of these charges are specified in terms of that one coordinate system. Maybe the Cartesian coordinate system, right? It's at some XYZ. So the first one's at some XYZ, the second one's at some other XYZ. And you want to find the electric field at some third point, some different XYZ. The principle of superposition applies. What does that mean? Well, that's just, superposition is just a fancy way of saying you can consider each separately and individually and then add the results together. And add in this context, because E is a vector, you're adding things in terms of their vectors. So you can kind of see from these arrows up here, like Q2, so P is the point at which we want to figure out what the electric field is. So Q1 is going to have an electric field that's pointing in that red arrow direction that says E1, because it points away in all directions, right? From Q1, if it's a positive charge. It's pointing away in all directions. We don't care about all directions. We care about one particular point P. At the point P, the electric field is going to be pointing in the direction of E1. Then we got Q2. Q2 also electric field going away from it in all directions, but we only care about P. That's going to result in the kind of cyan, light blue E2 color. The total result is the vector sum of those, which is E in the blue or purple, okay? So this gets a little more complicated here. So what was our original Coulomb's law? Was E equals R hat, then it was Q divided by 4 pi epsilon R squared. That was our original, the simple one. And then what we're saying down at the bottom here is, well, if we have 2 point charges, we got to add them together and we're left with this stuff, and that looks a little uglier. If we break it down and we just look at E1 due to Q1, and you kind of compare it to the top right, like the basic Coulomb's law, you might go like, wait a second here, like now we got a cubed in the bottom, right? We got a cubed, we got these absolute value signs. We do have a Q, and we do have divided by 4 pi epsilon, like that one. But the rest is, it could appear like a bit of a mystery to you. I forget in the book, I feel like the book might kind of gloss over this kind of quickly. So we want to just talk about why this is. Well, what do we care about? We care about the distance between Q1 and P. If we want to figure out E1, we care about the distance between the charge and the observation point. In the one at the top right there, the basic one, the distance is just something called R, okay? And you square it in the denominator. Here, this distance, well, this vector is represented by that R minus R1. So the equivalent to the top right there, the R in the bottom, is going to be the magnitude of R minus R1. Okay, so it's kind of like saying, so our magnitude of R minus R1 is kind of like saying R equals the magnitude of R minus R1. Does that make sense? Does that seem a bit mysterious where that comes from? So kind of think about it like back here, we wanted to figure out what the electric field is at point P. That distance between the point charge and P is R. Well, all that we care about is the distance between the charge and the observation point. In this case, the distance between the charge and the observation point is the magnitude of R minus R1. So that's where these absolute value signs come from in the bottom. But then you're still like, well, what about the cube? Like in the top one, it's squared and like what's going on? Well, we have to take into account this part of it, the R hat. What does that really mean? It means we need a unit vector that's in that direction. How do you get a unit vector? Yep, the vector divided by its magnitude. So it's like we're saying R hat, it's the vector divided by its magnitude. Okay. Now, note that there's an R squared in the denominator of the basic form of Coulomb's law. So really we need to square that. Okay. And then we have R hat upstairs, like outside, right? So what we really have is R hat, which is R minus R1, R minus R1. These are all vectors. And then we're going to be multiplied by a Q, I'll call it Q1, divided by 4 pi epsilon. And then we have the magnitude of R minus R1 squared, because that is what our R is. So if you look there, we have an R minus R1 magnitude. Here, we have an R minus R1 magnitude squared. That's where the R minus R1 magnitude cube comes from. And upstairs, we are left with an R minus R1. That's where that comes from. So they're really the same thing. It's just in a more complicated form because we're not considering the charges to be at the origin because we can't, because there's multiple charges. Okay, so basically you do that for each one, R minus Rx, right? Where X is 1, 2, 3, whatever. And you end up with this. Now this is specific for 2 charges, but as you might guess, we could take the next step, complicate Coulomb's law a little bit more. And now we can have it for any number of point charges. Very common, there's a question like this on a midterm or a final, that sort of thing. So we'll look at an example of it. They're normally not that difficult, but you would be surprised at how many normally simple mistakes are made from it. Okay, so this is for any number, I equals 1 to n, where I is the individual charge number, like I equals 1 here, I equals 2 here. Qi, that's like Q1, Q2, R minus R1, R2, R3, right? Okay, let's do an example. 4 charges of 10 microcoulombs. Each are located in free space. What does that tell you, the free space bit? Why is that important, or what does that mean in terms of your equations? Like, we're going to use this one, right? Because there's a bunch of point charges. What does that tell you? Yes, which tells you epsilon R equals, yep. So basically it tells you epsilon right here is going to equal epsilon naught. Okay, that's what the free space bit tells you. So we got 4 charges. You can see them, they're in blue down at the right, the figure in the right. We are given their Cartesian coordinates, their XYZ, right? -3, 0, 0 means X equals -3, Y equals 0, Z equals 0. X-axis, you can double check, X cross Y equals Z, so that all checks out. The X-axis, the first one it says is at -300, which means X equals -3. Positive X is in this direction, so negative X is in this direction. That's why that one's right there. That would be at -3, okay? Next one is at 300, that means plus X. So, right, X equals 3. That's why that one's Q2, that one's at 3. 0 minus 3, 0, it's X, Y, Z, so Y equals -3. Positive Y is this way, so this one's at -3, that's why it's Q3. And the last one, 0, 3, 0, that's that one. They're all in the XY plane, they're all at kind of plus or minus 3. Find the force. So we get to use what I just said, how, I said we could sometimes look to find the force of things. The force on a 20 microcoulomb charge located at 0, 0, 4, XYZ, so Z equals 4. That's this one right here. All distances are in meters. What direction do you think the final answer is going to be in? The force of the test charge, Q, at 0, 0, 4. Anybody have a guess at what direction it's going to be in? Yep. And what makes you say that? Right. Basically, the ones in the non-Z direction, like the forces in the X and Y, will cancel each other out from symmetry. So think about that. Like think of what's easiest. Maybe like, so Q4 here, there's going to be an electric field that goes off of it and it goes in that direction. It's indicated by F4 here. But then there's going to be a Q3 and an associated F3. And so they're going to kind of cancel out the X or Y components and just leave you with the Z. If you can see these sorts of things beforehand, that's great, because then when you get the final answer, you can see if it makes sense. You don't have to though. Like if you just follow through the steps, you should come to that answer, okay? Okay, let's go back and look at our equation. First of all, ask for the force, but as I said, F equals Q times E. Q, in this case, is the charge that we want to find the force on. So it's 20 microcoulombs, okay? These Qs are the Qs that are generating the electric field. So this is one place where some mistakes are made, okay? So Qi, these are the 4 charges. So we've got N equals 4 right there. So we got to go through them 1, 2, 3, 4. 1 over 4 pi epsilon naught. We don't need to worry about that much. That's the same for all of them, right? Qi is also the same for all of them. It's 10 microcoulombs. We need to do R minus Ri for each of them. So we need to find out what is R and what is Ri. Ri meaning R1, R2, R3, R4. So R1 is minus X hat 3. Let's see why is that. Well, the R1, the way you need to think about that is if you drew a vector from the origin to that charge, what would that vector be? So if you drew a vector from the origin to Q1, that is going to be R1. Then you'd look at your axes. Oh, positive X is in the opposite direction to that. So it has to be in the minus X hat direction. What's its magnitude? That's just its length. It has to go 3 to get to Q1. That's why it's minus X hat 3. For Q2, exactly the same thing, but we're going in the plus X hat direction. Q3 minus Y hat, right? Minus Y hat 3, and Q4 plus Y hat 3. Those are the numbered R's, the RIs, the R1, 2, 3, 4. We also have just a regular old R here. The R is from the origin to where you want to figure out what the electric field or force is. In this case, We want to find the force, which really means find the electric field there first, then figure out the force, or you can do them together. But we want to find it at 0, 0, 4. So we need to figure out what is the vector from the origin to 0, 0, 4. That's straight up. That's in the z hat direction, and its length is 4. Once you do that, the question is kind of done. Like, you just have to go through the steps. We just need to plug them in the equations. So with these in mind, let's just plug in the equation. I've got the equation for E up at the top right. Okay, so let's look at it slowly here. This is doing both at once. Remember, F equals Q times E. So if you said, well, just imagine that that Q's not there, then it's just the electric field equation, okay? The only difference here is going, instead of it being a two-step process to figure out E, and then at the end of it, multiply it by Q, the 20 microcoulombs, this is doing it all together by just putting it in the equation, okay? So up top right, we've got 1 over 4 pi epsilon, and the question said it was free space. That's why we've got epsilon naught. The QI here is this capital Q1, which is going to be 10 microcoulombs because it said all of them, all 4 charges are 10 microcoulombs. Okay. Then we have R minus R1. We already started off by defining all of these R's. So R is Z hat 4 minus R1. It'll be minus X hat 3. So it'll be plus X hat 3. We got a 125 down here. Someone tell me how that is 125. Which would be what? Let's start out with the magnitude. So it would be R, so we got to get the magnitude, right? To get the magnitude, we do the sum of the squares and then we take the square root. Okay. Exactly. Yep. And if you're wondering where the 5 came from, well, this is what the R minus R1 vector is, right? And so if we wanted to, so we're saying basically R minus R1 equals Z hat 4 plus X hat 3. So if we want to do the magnitude of that, we would go the magnitude of R minus R1 is the square root of 4 squared plus 3 squared. It's squared. 4 squared is 16. 3 squared is 9. 16 plus 9 is 25. The square root of 25 is 5. Then we have to cube it. 5 times 5 is 25. Times 5 is 125. That's where the 125 comes from. Then you can multiply 125 by the 4 if you want. To give you 500, you still have the pi epsilon naught. And you still have the Z hat 4 plus X hat 3. All right, next one. What changes? Well, Q doesn't change. Q2 is actually the same as well. 4 pi epsilon naught doesn't change. The only difference is it's R2. R2 was the opposite sign to R1. So when we do R Z hat 4 minus R2 X hat 3, now we've got a minus sign here. The magnitude doesn't change though, right? Because it's 4 squared plus 3 squared square root. So it's still 125 down here. Still times 4, still 500. At the end of the day, the only difference is that minus sign, which goes right there. And look at the early prediction that we had. We said all these things, the X and Y's will cancel each other out. And if you just look at these two, which are on opposite ends of the X axis, because right here, we're just looking at that one and that one. And we're saying that each of them generates a force that has a Z component and an X component. The X components cancel out. We're just left with the Z component. Okay. Okay. Let's look at the third one. So we're going through this, right? We're going I equals 1, I equals 2. Now we're at I equals 3. So we're using Q3, but all the Q's for this example are the same. They're all 10 microcoulombs. And we're using R minus R3. R, Z hat 4, minus Y hat 3, plus Y hat 3. This is the same magnitude as the top one, right? It's still 4 squared plus 3 squared square rooted. So it's still 125, still times 4, still 500. The only difference is here we have a plus again, and now we're dealing with y hats because the R3 is in y hat. You could probably guess the last one. The only difference is the sign again. We have a minus because we have a minus here. The reason we have a minus there is because we're doing R4. R4 is y hat 3, not minus y hat 3. So when we do R minus R4, it's z hat 4 minus y hat 3. Boom. We've got that. Now, our total force, remember I said superposition applies for electric fields. That means to get the total electric field, you can do E1 plus E2 plus E3 plus E4. Same thing with the force. You can do that as well. So you can do F1 plus F2 plus F3 plus F4. If you added up all of these vectors, note that all the Q1 to Q2 through Q3 to Q4 are all the same. They're all 10 microcoulombs. So that means this whole outside coefficient is the same for all of them. If you added up those vectors in the brackets at the end of it, you'll have, well, what would you have? Just from the parentheses ones at the end here. Yeah, you'd have z hat 16. The x's would cancel out, the y's would cancel out. Here's the total result here. We still have our 500 pi epsilon naught. We have the z hat 16, like you just said. And if you're wondering where that number came from, that is q times, I'll say qi, okay? Where q is our test charge or our location where we want to figure out what this is. That's the 20 microcoulombs, okay? I'll say Q1 equals Q2 equals Q3 equals Q4 equals the 10 microcoulombs, okay? So we have 20 times 10 to the minus 6 times 10 times 10 to the minus 6. 20 times 10 is 200. 10 to the minus 6 times 10 to the minus 6 is 10 to the minus 12. So you end up with this, at which point you can just punch into your calculator. End up with that. Any questions about this one? As I said, it's not uncommon to see one of these in the midterm 2 or the final, so feel free to ask me now. Yeah.
So it's only going in the same direction because all of the x's and y's.
Exactly. If we messed up one of these, like if we said, I'm going to move one of these charges around, even if I just moved Q1, instead of being at minus 300, I made it minus 200. Now we'll have an x hat component. Yep, it's just due to symmetry for this one. Any other questions? Okay, so let's go the final step. What did we do? We started with Coulomb's law for one charge. Then we went to 2 charges. Then we went to n charges. Now we're going to go to this nebulous charge distribution. That's some blob of charges. The charge distribution could be anything on it. The shape of this volume could be anything. And we want to be able to figure out what the electric field is due to this. So this is a continuous charge distribution instead of those discrete point charges being at particular locations in space. Okay. We got some volume charge density in this thing. And how do we handle it? Like the way we handle a lot of things in this part of the class, we break it up into little pieces. So just so you can remember, our normal, most basic Coulomb's law is this. That's a vector. That's our most basic form of Coulomb's law. Now, if we consider some tiny piece of this volume, we consider that piece to be this little red cube. It's a tiny little cube of the volume. And we essentially treat that as if it's a point charge. Okay, it's not. But if you imagine that as your point charge, then you'd go, well, my electric field due to that point charge, what would it be? Well, it'd be pointing away in some r hat direction, directly away from it, right? Like that. We'd have whatever its charge is. That's the magnitude of the charge in coulombs. Here it's some differential amount of charge. Okay. Still a charge, but it's just the amount of charge located in this little red box, this differential volume. Okay. Still have our 4 pi epsilon, and we still have our r squared, just like up here. The difference is this is the total electric field due to that point charge Q. Down here, this is the differential amount of electric field due to this differential volume of charge dq. Okay. So we want to break up our volume into a whole bunch of tiny little pieces of volume that make up the overall volume. We want to figure out the contribution to the electric field from each of those little tiny volumes. We add them all up, basically. That gives us our total electric field. Now you'll notice some primes here. We've got an r hat prime and we've got an r prime. The reason that's there is because just remember what we're doing. We're also later going to come up with another cube over here and then another cube over there, right? And one over here. All the cubes that make up the entire volume. And when we consider each one of them, each one of them is going to be pointing in a different r hat direction, and the length of that vector is going to be different. So the primes really just represent, that's for this particular segment, this particular dV that we're considering. So you can probably guess what's coming next when you've got some dEs and dQs and that sort of thing. We're going to integrate this to get it so it's over the entire body, the entire volume. Before we do, you can see the dQ here, which really is representing the Q in the original equation, Coulomb's law. But using what we were talking about before, dQ can be represented by rho v dV, okay? Why is that? Well, you could argue it in terms of units if you want, how the units make sense. Coulombs per meter cubed times meters cubed, right? You could argue it just in terms of that it makes intuitive sense. If you have a certain amount of coulombs per meter cubed and then you multiply it by meters cubed, it's the amount of charge in that volume, right? But the important thing here is to switch it, because ultimately we want to integrate it over the entire volume. If we want to integrate it over the entire volume, we need a dV explicitly in the equation. We can't do it in terms of dQ directly. Once we have it in terms of dV, now we can take the integral of both sides. Okay. And this is what we're left with. So we have the total electric field being the integral over the volume V of all of the dEs. Okay, so it's like you break up this body into a tons of little pieces and you figure out the little contribution of each little piece to the electric field at the point where you want to know what it is. And if you do that integral where you consider all of them, you get the total electric field. So we have our 4 pi epsilon here that come out front. So again, that's just that, right? The 4 pi epsilon. So that comes out front. We have an integral over a volume. We have our r hat prime, meaning the direction from the particular piece you're considering to the observation point. Rho v dV, and the distance between your particular point you're considering to the observation point. This is for a volume distribution, but you could do the same thing with the surface and the line. The only difference is, instead of integrating over a volume with dV, we integrate over a surface with ds. Instead of rho v, we have rho s. For the line, the front part's the same, but we're integrating over a line. Instead of rho v or rho s, we have a rho l. Instead of a dv or a ds, we have a dl. This, in all cases, is the distance from that piece you're considering to the observation point. The piece, well, that could be a piece of volume, a piece of surface, or a piece of line, okay? In terms of volume, you can visualize it as a tiny little cube. In terms of surfaces, you can visualize it as a tiny little square. As a line, you can think of it as a tiny little segment of line. So this is our first way to calculate the electric field. We got Coulomb's law. We're going to have 3 ways to calculate electric fields. Within Coulomb's law, we got point charges, we got multiple point charges, we got continuous charge distributions. The first 2 use the more familiar forms of Coulomb's law. The third one, well, it's still regular Coulomb's law, but now it's integrals. And then within that one, you could have a volume, surface, or a line. The next way to calculate electric fields that we're going to cover is Gauss's law. Gauss's law was also the first of the Maxwell's equations, the divergence of D equals rho V. The third way that we're going to learn, and all of these will probably come next week, we'll probably get through all of them next week. The third way is electrostatic potential. We'll define what that is, and we'll talk about how you can calculate the electric field from it. So we're going to have the 3 ways to calculate electric fields. And when we get to magnetic stuff, we're going to have 3 kind of similar ways to calculate magnetic fields. Okay. Okay, so we'll probably, let's see how much time we have. We got 10 minutes, so we should have enough time to finish this one. So, ring of charge of radius B has a uniform line charge density of positive polarity rho L. Okay, so we got to break that down a little bit. We got a ring. You can see the picture of the ring. It's got a radius of B. All right, remember that. We're going to use that. The radius is B. This ring is centered at the origin. It's in the XY plane. It doesn't tell you that it's in the XY plane, but you're free to kind of put it wherever you want to, right? Uniform line charge density. Well, first of all, you look at this and you probably first ask yourself the same thing we asked ourselves last class, I think, which was, is this really a line charge? Because this looks like a 3-dimensional like structure here. It's got some volume in this thing. We're considering it to be so thin that it really is just a line, and you're reinforced by that. That's reinforced by it saying it's a uniform line charge density, and it's giving rho L. Those are all hints telling you you can assume this thing is so thin it's like a line. Okay. The ring resides in free space. We know what that means. That means the same things that meant in the last example. Epsilon equals epsilon naught. Determine the electric field intensity, E, at a point P equals 0, 0, H along the axis of the ring at a distance H from its center. These questions in this part of the class are going to get a little wordy. They are going to require you to get a mental model, a visual image of what's going on. Sometimes there might be a diagram presented, sometimes maybe not. For midterm 2 and the final exam, I don't want anyone to not be able to do something on a problem because maybe I didn't give the best description of it. So what I'll say is, if you need help understanding the setup of the problem, put up your hand during one of those exams and I'll help you. Okay, I won't help you solve it, but I want to make sure you have the picture correct. Then it's up to you to actually solve it. Okay. Okay. We want to determine the electric field at that point. Any guesses what it might be based on our last example? What direction at least it might be in? What was our last one? We just had a point charge there, a point charge there, a point charge there, and a point charge there. Yep. See, when you realize those sorts of things, you can make your life a little easier. So we'll use that. Basically, all of the pieces going in the R hat direction are going to cancel each other out, as we'll see. Okay, so let's do this. The setup of these problems is kind of half the battle, maybe more than half the battle. All right. So here's our problem. We got to use Coulomb's law. You'd go, well, this is a continuous charge. It's not like discrete charges. If it's something's continuous, that means it's going to be an integral. It said it was a line charge. That tells you what formula you need to use. You need to use the version that is continuous for line charge distributions. So what is that one? That is, just going back here for a second, that means it's going to be that one. It's a line charge distribution. So let me write that. So it's E equals 1 over 4 pi epsilon integral over the line L r hat prime rho L dl prime divided by r prime squared. Okay, first thing we got to do, let's just consider this green highlighted piece right here. Okay, we're just going to consider the green highlighted piece. And if we're considering just this piece labeled number 1 here, the vector that we're worried about, remember, we're always worried about the piece to the observation point. If it's just a point charge, then it's just the vector from the point charge to our observation point. In this case, we're just considering this green 1 here. So we're just at this point worried about the R1 prime. So if you got this problem, even if you didn't know where you were heading yet, it'd be a good idea to write down what R1 prime is. You need to break it down in terms of the vector components. So we probably want to use the cylindrical coordinate system here because it's kind of a cylinder. Okay, so if we did this, we would want to represent R1 prime in terms of those variables. Okay. What are the 3 variables in the cylindrical coordinate system? R phi z. Okay. So we can represent R1 prime in terms of R hat and Z hat. Let me write it down and then I'll explain why it is this. So remember that R hat points from the origin outward in the XY plane. Okay. So this one, it should point from here out to here, but we have minus R hat. So it's pointing inward. The magnitude of that is B because that's our radius. So essentially what we're saying is we're coming in minus R hat B, then we're going up Z hat H. Those are the 2 vector components that give us R1 prime. That's maybe the trickiest part of this problem. Setting it up that way. Because once you have that, then you can get the magnitude of R1 prime. What would it be? It would be, remember, the component squared and then square root. So it would be the square root of minus b squared plus h squared. So that would just be square root of b squared plus h squared. Okay, and we can also get the unit vector, R1 prime hat, because it's just the vector divided by the magnitude. Okay, so we can start to plug some things into the formula here. What we're really trying to figure out is dE1. The piece of the electric field, the small differential piece of the electric field that is being created or being caused by this little green segment here labeled 1. So we have 1 over 4 pi, and it said it was in free space, so I can write epsilon naught. Now, we're not doing an integral yet. We're going to do that eventually, but right now we're just considering this one green segment, this one piece. So what do we have? Well, we've got the unit vector. So that's going to be the R1 prime hat. And then we have the rho L dl right from up top here, rho L dl. We just did this one. We're eventually going to do the integral, but we're just considering a dE right now, not the full E. That's why we have this part, but we don't have the integral yet. We have that part. We just wrote the rho L dl, and then we need to divide it by the magnitude of R1 prime squared. Okay, it's 4:44. So I think we should probably stop there, and I'll pick it up at this point on Monday. That will finish off this set, and then we'll move into Gauss's law and electrostatic potential on Monday. We should finish those next week, and then we'll move on from there. So have a good rest of your week, good weekend, and I'll see you all on Monday.